Hello there, my name is Max Merlin. I'm a PhD student at Brown University, and today I'd like to share with you my work on locally observable Markov decision processes. As a roboticist, I care about having robots that can autonomously perform tasks such as making an omelet or taking out the trash. And these robots will need strong decision-making skills in order to choose what actions they sequence together to achieve those goals. Unfortunately for robots and for me, this is a difficult problem for a number of reasons. One of the main reasons for this is that robots have limited sensing capabilities, so the world state that they are in cannot be directly observed. The typical framework that we use for representing an environment that we can only receive limited observations about is called a partially observable Markov decision process, or POMDP. The POMDP represents a domain in which a robot can take actions which change the world around it, and in return receives observations of the world state through its sensors, as well as a reward signal. Unfortunately, POMDPs are so generic that in practice they become extremely difficult to solve. Having to plan through a belief of possible states causes a huge explosion of complexity as domain size and task length increase. Even though POMDPs in their most generalized form are computationally intractable to solve, humans and many other animals are quite adept at making decisions in partially observable environments because we live in one. Therefore, we are interested in understanding and formalizing the structures that we can add to the POMDP definition to make it more tractable for planning. For example, we could say that the world is composed of objects, which gives us an object-oriented POMDP. Also, as mentioned before, robots are reliant on sensors to observe the world state, but those sensors are limited by both range and physical obstructions. Moving the sensor to be nearer to an object or to look around an obstruction will facilitate the ability of the robot to estimate that object's state. So, we can say that there is an area that is local to each object, from which its state can be determined with high accuracy. We also assume that our robot will be able to observe all of the relevant objects required to complete a given task. Our hypothesis is that given those assumptions about our domain, we can plan efficiently by reasoning about the locations to move the robot that will facilitate these observations. We have adopted this structure and formalized these assumptions into the locally observable Markov decision process, or LOMDP. Our tuple includes all of the elements of a standard POMDP tuple, but with the addition of a new element that can represent this spatial component, which we call locality. We define the locality for each object as the set of all possible states from which that object can be observed. Each position that the object could take implies a different set of robot states from which that object could be observed, so we can take the union of all of those states over every possible object location to find the full locality for a given object. With this information, we can search for an object by navigating through the states from which it could be observed. Additionally, because reaching the locality of an object guarantees accurate observations, once the object has been observed, its state becomes fully known, and it is no longer necessary to maintain a belief over its state. With this new model that can represent localities, we have developed a new planner that is able to exhibit some unique behaviors. Consider a home service robot that needs to make a sandwich. It will need to get all of the ingredients out from their storage locations in the kitchen, locations that are likely not known at the start of task execution. In this simplified example, instead of maintaining belief over every possible location that the bread could be in, shown in the figure to the top right, the robot can instead maintain the much smaller belief over where it might need to move in order to observe the bread, as shown in the figure on the bottom right. Because there are areas that the robot could move to which allow it to see the bread in many different positions, this has the potential to reduce the search space significantly. Or consider that the bread may be in any location inside a given cupboard, or it could be behind items that need to be moved out of the way. A standard POMDP would need to model every possible configuration of the cupboard to complete a plan, whereas our planner, much more like a human, is able to delay planning how to interact with the bread until after it has searched in a cupboard and observed the bread, because we can guarantee that the bread will become fully observed once we enter its locale. In this example, the plan that we generate includes looking for the bread, but it initially only plans to move to the locality marked A to search. Upon reaching that locality, the robot does not observe the bread, so it adds a move action to locality B. From locality B, the robot can now see the bread. Because the state of the bread is now known, the robot can add to its plan that it needs to move closer to the bread, and then pick it up, after which it will be able to continue with its original plan and slice the bread. If you have any questions for me, please feel free to send me an email or contact me on the ICRA Slack channel. Thank you so much for your time.